In this third of 4 chapters on Fourier theory, we consider the kinds of functions that actually appear in computers. Because computers are discrete and finite collections of bits, or even qubits, we don't have continuous anything. There's no real number line. There are only finite arrays of complex numbers, that is, vectors in Cn. So we take the Fourier transform of the previous chapter and formulate a finite sum that approximates our continuous Fourier transform at n sample points. And we end up with a nice computable map from vectors in Cn to other vectors in Cn. That's our digital Fourier transform, or DFT. Once we commit to making that change, nice things happen. Not only do integrals dissolve and turn into sums, but the pure frequencies e to the isx that we used to build our functions turn into roots of unity. Remember roots of unity from the first week of class? As I admonished in the last chapter, don't fall into the trap of starting with the definition of the DFT as a formula. Instead, consider a general vector function that we want to build, little f sub k, and ask the question, how can we formulate that as a weighted sum of roots of unity with coefficients big F sub j? That question leads to a formula for computing those weights, and that formula is the definition of the DFT. This way, we come about the meaning naturally, and we instantly see both directions. We know how to compute big F from little f and little f from big F. Since we're now working in a finite vector space, we can view the DFT as a simple matrix transformation. After all, functions are just column vectors, so mapping a function to its digital Fourier transform is nothing more than subjecting its vector representation to matrix multiplication. Well, the matrix is going to be brilliantly simple because this whole theory is beautiful. It just consists of the roots of unity raised to different powers. The properties of the DFT all derive from the continuous Fourier transform. If you studied those properties last time, you'll see their discrete alter egos here. Otherwise, you can just consider today's DFT properties as self-contained results and refer to them as needed, which, by the way, will be both in the QFT tomorrow and Shor's period finding next week. A useful takeaway from today's lesson is the visualization of the DFT. The DFT is sometimes called the spectrum of the function. If the original function is, say, some digitized audio signal, the DFT is the distribution of frequencies of that signal, high-pitched oboes and sopranos, and low-pitched basses and tubas. But for us, the real gold is this. By graphing the spectrum vector, we can often glean whether or not there's a hidden pattern, some frequency that dominates the function, implying a kind of repetition. I hope this flips on a little LED in your head. It suggests periodicity in our original function. On the other hand, if no such dominant frequency shows up in the spectrum, the function probably has no periodicity. This is the driving observation of Shor's period-finding algorithm and motivates the use of the quantum Fourier transform in its accompanying circuit. 2/3 of this chapter is a fairly mathematical and computer science-y development of the computational form of the DFT, namely the FFT, or fast Fourier transform. It's eminently skippable, but has value in the design of the QFT circuit tomorrow. So if you have time, give it a shot. No loss if you don't. By the way, I often tell students in beginning computer programming classes that recursion is nice, but it can also be dangerously inefficient. If you happen to read the development of the FFT, you'll see how true this is. The recursion relation that we use as a simple implementation of the DFT is the slow way to go. It's not until we unwind recursion and replace it with a non-recursive iterative loop that we actually get a useful, computable, fast Fourier transform.